So we're talking about leading edge erosion on wind turbines, predominantly caused by rain, but as you'll see, it can be caused by many other things as well. If not checked and controlled, it will cause structural integrity problems, which can be very, very severe indeed, and can cause the entire blade to need to be replaced. Obviously, if you need to do a major repair on a blade that's not part of a normal part of operations and maintenance schedule, that's causing a lot of loss of energy, and that's loss of revenue. And in fact, it's believed that leading edge problems on blades are now the biggest blade issue there is, probably accounting for some 50% of all uptow costs on blades. And if that's offshore, it's probably more than that. It's probably up to about 65% of all blade costs is managing leading edge erosion. Reckoned to be about $1 billion US by the end of the decade. So it's a huge, huge issue. So, you've seen this diagram before? Sorry about that, but it is a good one. So, mainly it's rain that causes this issue, but anything else is just worse. Okay, so if it's in a rural location, you could get dust, sand, insects are really bad as it happens. Offshore, you've got worse conditions, obviously, than on land. There's a higher instance of sleet and hail. Large hailstones can cause lots of issues. And also the droplet size can vary in different locations. So a small droplet of rain causes less problems than a large droplet of rain. So if you happen to be situated in a tropical country, the effect of rain erosion can be a lot greater. Salt spray is particularly bad. So if you've got over 3.5% salinity, you're going to get about 40% greater erosion rate than you would get just from rain. So anything that's whipped up by the blades is really, really bad. The other thing is it's very much related to impact velocity. So the impact velocity is the speed at which the rain comes down, the speed of the prevalent wind, and the speed of the blades. So tip speeds have been getting faster and faster. Onshore, it's rare to find anything that's much below about 80 meters per second. It used to be very much limited by noise regulations. Obviously, if you go offshore, that's not such an issue. So typically offshore, 100 meters per second is quite normal. So the impact velocities are getting higher and higher. And its relation to rate of erosion is to the power, to the fifth power. Okay, so it makes a massive difference as that tip speed comes up, and people are only just starting to realize that, which is why a lot of offshore turbines that were designed for 25-year life are finding that their leading edge erosion problems are starting after about 2 years. And they've got a, you know, this is a big, big, big issue. Also offshore, you tend to get more rain. So that relationship is about 2/3. So that's also having an issue as well. Right. So I think you've seen a diagram similar to this. The tip is what gets the rain erosion the most. You do get issues throughout the blade surface, but it's where that impact velocity is the highest that it's worse. We typically, when we're talking about leading edge protection, you're talking about a maximum of about 10 meters towards the end of the blade. It can be anywhere between 5 and 10 meters in reality. And you're normally looking at about 4.5 centimeters in from the tip of the leading edge. And in terms of the thickness of the coatings, you may be up to 2 millimeters thick, going down to maybe 0.1 millimeters as it touches the rest of the inner blade. Now, we all know turbines are getting bigger. I've just told you that it's a factor to the power of 5 with tip speed. The bigger turbines all run bigger tip speeds. Why do they do that? Because you can reduce your drive chain size by about 30%. bigger rotational speed, less induced torque onto the drivetrain. That reduces cost. It reduces likelihood of gearbox failure, drivetrain failure, etc. So there's lots of reasons why they want to increase the tip speed, and unfortunately, that acts on our leading edge. You see this diagram, which is a portion of the diagram that Edvard showed you earlier on. It's showing that by 2035, we might be hitting 17 megawatt turbines. Well, I was speaking to someone from SSE last week at the Global Offshore Wind Conference. They're already ordering 22 megawatt wind turbines to be installed in 2027. Vestas have got on test, as we know, their V236. It's a 15 megawatt turbine. The height of this one is shown as 151 meters. That's 281 meters, the big Vestas. It's on test at the moment, producing power. Siemens also have a 236 meter, which is the swept diameter, at 14 megawatts on test. These things are getting bigger and bigger and bigger. The problem's getting bigger and bigger at the same time. Did we see this one before? Probably one similar. So, most repair of offshore blades, in fact, all repairs of offshore blades, apart from research projects, are performed manually. Offshore, you've got a reduced weather window. You can't send people up in much more than about 10 meters per second winds. You can't send them up in more than a 3-meter swell to actually land on the wind turbine itself. So the days when you can actually do repair are quite short. And then you've got to reach all the conditions for actually making a good repair. You know, your humidity levels, dew points, and all that sort of stuff have got to be right too. So the actual days when you can do a good quality repair are quite short. And to answer your question earlier on, Dave, how do you check the quality of a manual repair? How many coating inspectors are ERATA qualified and happy to dangle 200 meters in the air from a wind turbine blade? You know, they're reasonably hard to find. Crane ships, to actually get people on, people can correct me here, but I believe it's about $1 million a day. So that's not good either. And there are some robot technologies out there, but none of them so far can be deployed offshore because they all require to be tethered. And just doing that is very, very challenging. And obviously, the bigger the turbine, the bigger the loss of energy when it's not going round. So this is what they do. Normally work in teams of 2. They are all ERATA qualified. There is not many of them. There are nowhere near enough ERATA qualified coating applicators for what's required. And as the problem is getting bigger and bigger and bigger, there's only so many people who are happy to even get that qualification. You know, most people do not want to do it. It is incredibly dangerous. It may be 10 meters per second when you go up, but winds can change, weather conditions can change, and it is a very, very dangerous activity. So it typically takes about a day to repair a blade, if you're lucky, if you've got ideal conditions. You have to grind the surface finish. Obviously, I'm going to talk a bit about that damage in a while. But if we just consider that it's not too challenging, they have to grind the surface, do a sort of an abrasive grind, then a fine grind, then thoroughly clean it. Then they've got to apply the coating, all the while dangling, and hoping to get a constant thickness, etc. It then has to cure. They typically apply the coating on all the blades very rapidly at the same time. They shift it into a vertical position. They apply a pin lock so that the blade can't rotate at all. So someone else has got to go into the drivetrain to apply that. You're talking 4 or 5 days, maybe a week to repair using a manual process. So this is what ReBlade are developing. This isn't available, this product yet, but will be next year. It is basically a UAV. It's a drone that is a factory. So it's got a U-shaped hull, and it literally flies up onto the blade. It's got all of the operations within that hull structure, and it can do 4.5 blades in half a day easily, and that includes cure if it's using a rapid curing coating, and I'll talk about that in a second. So you don't need to be able to transfer people on, so you don't need a transition zone, you've got no wires or anything else holding it on, and it's assisted by AI to maintain the quality of the coating, so it's far less variable than a manual operator, and it's landed using machine learning, so it lands onto the blade under automatic control. So a little bit about damage levels. So there's 5 categories, and if you ask people to identify what type of damage is in what category, they're a bit like economists, you'll get a variety of answers, very few which will be corresponding to each other. But generally recognise Cat 1 is the lowest form of damage. It just looks like dirt. It's almost impossible to actually distinguish that it's not a perfect coating because they get dirt on the blades anyway. You can't really detect it from the power curve. It's going to have very little difference to the energy output, probably about maybe 1% or something like that, which is in all the other variability. So it's very hard to detect. It gradually becomes category 2. This is also what you'd class as cosmetic. It hasn't gone through that top coat or leading edge protection, but you can see it visually now. Okay, and I would say that image on the top is category 2, and people may disagree with me. That can cause an annual energy production loss of about 2%. Okay, but again, you probably won't detect that in the power curve figures or the energy production figures, because there's too much other variability going on. Okay, so unless you're looking for it, and because this is happening over a couple of years, you will not detect it. Then it starts to get a bit more consequential. You enter category 3, and this is where you've gone through the top coat, you've gone through the gel coat, and you've now exposed the underlying structure, the laminate structure. You're starting to see fibers. This is what we'd class as minor structural damage, and at this point, the non-linearity really kicks in, because the first stage can take quite a long time, and it will vary from blade to blade, turbine to turbine within the same wind farm, and obviously across from wind farm to wind farm, different manufacturer, different manufacturer. It's really, really, really hard to predict when it's going to kick in. But once it goes to Cat 3, it will rapidly progress to Category 4. And Category 4 is when it's actually started to go through maybe the first layer of laminate. When it's gone through the first layer when it's exposed the laminate, so it's entered Category 3, you've got about 6 months to repair it. That's what's recommended before it becomes quite catastrophic. Once it goes through a laminate layer, they recommend about 3 months to repair it. Once it's gone through a whole structure, you've got to stop the turbine quickly, and you're probably looking at a full blade replacement, which would be anywhere from about 300,000 US on a small blade onshore to over $1 million if it's offshore, and it's one of the more modern wind turbines. So I would say that second image there, you're probably looking at about Cat 3. That's starting to get quite significant. And people say, you can't see anything, and then it looks like a shark attack on the blade. It suddenly happens much, much worse. So once it's gone through that top coat and you've started hitting structural damage, it's not a matter of just replacing a top coating. You've got to actually perform a repair. And this is where the problems really, really kick in. Because once that surface coating has been gone through, you're never going to get a repair quality which is as good as you had in the factory. And typically, they don't last longer than about 2 years, and they can fail within 6 months. There's so many variables. It's so difficult for the operator to actually effect a repair like that when they're dangling from a rope. There is no one to check the quality of their work. Even the same operator will do 2 different repairs to different standards, but they're very, very rarely anything like as good as they would be when the patch was designed in the laboratory. And then you've got a constant maintenance issue with that wind turbine. As this can happen within the first 2 or 3 years, and you've got a 25-year lifespan on that blade set, you know, this is a really, really expensive problem that you're going to take on. So what can we do by the drone? So the drone is designed to do up to about category 3. Much, much better to repair at category 1 or 2. It's faster, you're going to get a much better repair. We can't repair delaminations by drone. You might be able to do it. Some of the other crawler robots may be able to do this in the future. But you really want a low-cost solution that can repair the damage before it becomes anything like structural. And there's no reason, if you had a regular maintenance program, why you'd ever see type 3. So within the drone, once fully developed, it will carry 4 modules. The first one is a grinding module, and this is custom designed, super, super lightweight, and it will do a very sort of coarse, abrasive grind, and then it will do a finer grind. You then use air to blow off all the dust, and then you then wash under pressure with a solvent IPA to make sure there's no static holding any particles on, and you then apply the coating. All this is done at about 5 meters per minute. So it happens in one operation as the blade, as the drone traverses along the blade. I haven't embedded a video into this, but if you come upstairs, I've got a video showing you this happening. And the drone just basically lands on and it flies itself along the blade. It's got a very special clamping system which maintains a perfect alignment along the leading edge. You can use any wet LEP. So it's got a thermodynamically controlled sort of 2-pack system. And in fact, it's the only system that's able to do one of the fastest curing polyurethane systems out there, which is a Technos system. And it's quite smart how this works. You wouldn't be able to use the faster curing, as Edward said, you wouldn't be able to use the faster curing coatings, LEPs, with manual operation, because they just wouldn't be able to do the work in the speed that's required. So the actual repair process, you'd inspect beforehand the blade for sort of suitability, that the damage hasn't got too far, either by using one of the many sort of inspection drone services which are out there. There's ground-based inspection systems now which are becoming very, very good. You'd obviously check all your environmental conditions for suitable for the coating you're going to apply. You then push the blade into the horizontal position, with us. So when a manual worker works on it, or the other robotic systems, they do it vertically, but we do it horizontally, so the drone can land on it. You prepare the surface, and then you apply the coating, and then the drone just flies back. And as long as it's got about 2.5 meter square space, it can take off from anything. So it can use a low-cost vessel. It doesn't have to be anything expensive. So we can control the thickness of the coating mechanically. You could also detect the thickness that's being applied afterwards as well. If you use a very rapid curing LEP, and there's a research one that we've been working with by Technos that cures in an hour. It takes 2 minutes to do 10 meters of leading edge. You can do all 3 blades. The turbine can be up and running, within a couple of hours in reality, which means you could do many turbines a day. The drone has been designed to be under 25 kilograms, which is hugely challenging. There's a lot of carbon fiber on it. The reason for that is it drops under some of the SORA regulations. So at 25 kilos, because we're typically working a long way from civil, from residential buildings and things like that, you don't need to get official flight permission to the authorities. You don't have to write a 600-page document about why it's safe to perform that particular test. And it means that you can use the lowest class of pilot certificate, which only requires a 2-day training course. So it keeps all of the costs down. As I said before, the drone actually lands on the blade itself. In the future, we'll probably embed software that other people have developed so it can actually take off and land and do the whole operation on its own. There's already systems that do that. You can train just standard service personnel. So we're not going to operate this ourselves. We're going to let other service companies do it, and you don't need to have any special qualifications for it. So these are other systems. This is a hot area at the moment, so lots of people are developing robotic solutions. There are also platform solutions which attempt to make it safer for the operators, but all of these systems require tethering, they require a lot of setup. They are more flexible, so they will allow you to perform multiple operations. A lot of the other robotic solutions will repair cracks and look at de-icing operations and all sorts of things, whereas we're single focus. We just do leading edge protection. And say none of these other systems can be deployed offshore at the moment. But I'm sure people will find a way of doing it at some point. Edvard mentioned other systems, so all of these work by having a sort of some elasticity within them, which enables them to absorb the impact from droplets. There's tape typically supplied by 3M. The issues are that they tend to fail at the adhesive layer at the moment. I'm sure people will suss it out, but a lot of the shell systems are failing. They take a long time to install. It's quite complex, and they are failing. But I think long term, these will probably be quite a good solution. But the wet LEP is also getting much more advanced now. So very quickly, the business model is hardware as a service. So we don't operate the drones. The idea is to lease the drones, charge a fee per blade, supply all the consumables. So whatever coating is required to be used, we'll supply that in a proper dispenser, which just plugs into the drone. We make sure that the drone is maintained, and we do all the training of the teams that are going to use it as well. So generally, service windows improved by about 50%. Obviously, it's much, much safer than using a worker dangling from a rope. You're reducing your downtime, you're reducing your levelized cost of energy, and also you are saving a bit of carbon. The less time that the turbine is stopped, the less other carbon emitting sources of electricity you're having to be used. So the first product's going to come out next year. This is going to be a halfway house. So it's going to have the grinding module in it, and it's going to have the coating module, but it won't have the sort of fine surface preparation and cleaning. So that will still require an operator to be there, but it does mean you can use a more rapidly curing adhesive, and you can guarantee your quality, and it will treble the production rate of the workforce. You can do about 3 turbines a day. Sorry, 1 turbine a day, 3 blades a day. And then the full one with all 4 of the modules will be available towards the end of 2025, and I think that's quite conservative. You can do at least 2 turbines a day with that drone. Every inspection will come with a quality assurance report, videos of the damage before, verification of the work that's been done. You'll obviously have to record that all the environmental conditions were right before you applied the coatings and did the repair. And any other operator information will also be recorded there. So where we are at the moment, there's a ton of industry engagement, talking to a lot of wind developers, some of the very biggest, talking to all the OEMs, talking with a number of service companies, and basically the development team's just working flat out just to finalise everything and go through the testing. This is just a summary, and I think I'm out of time. Thank you.
Okay, have you got any questions? Hello, working? No? Try again. Hello?
Trevor. Trevor.
Chris, I'm intrigued here. You speak about cure.
Yeah.
What do you call cure in percentage terms?
I'm not going to try and give a detailed answer to that because I don't know. But it's been verified by the the coating manufacturers that we've been working with that for this particular very rapid curing one, 1 hour is actually fine to go back into full production. Normally what you would do is you would cure it just enough to be able to move the blades into the next position so you can treat the next blade, and then you wait for longer. And they do this at the moment as well with slower curing adhesives. You wait longer once all 3 blades are coated until you're happy that the cure's at a level that you can bring the turbine back into full operation. But as Edvard says, it's quite tricky to get these very rapid curing polyurethane protection systems working. And there's sort of, it's only by having quite a complex application process that's got to be done very thoroughly that you can use them.
How limited by weather are you to actually fly the drone anyway? Is there...
Oh yeah, you're limited for sure. But we're designing the drone to be safe to operate in 14 meters per second. So normally you wouldn't allow a person to dangle from a rope much beyond 10. So that's why the weather window's a bit bigger. Obviously, you still need all the other conditions to be good enough to be able to apply a coating. But yeah, and if the wind picks up, the drone will automatically abort. So it will just fly off and return back to base. But yeah, 14.
Can I just have if it does fly off and abort, then you're midway through the concourse, how do you then pick up on the down?
I don't know. You might need to go back and restart it again. It's only a 2-minute process anyway to do a 10-meter section. So you'd probably just wait for it to fully cure and maybe just grind off the portion you've done and reapply the whole coating in one go. You'd use a bit more coating. You typically use about 600 mils of each pack per leading edge. So you would waste a bit of coating, but I don't think it'd be a problem in terms of the repair and the time down.
Just a quick one, what's your battery life?
It's not super long because we're trying to keep it below 25 kilograms, but the battery pack's just a plug in. So it's long enough to do 3 blades. Yeah, yeah.
How do you plan to ensure coatings apply for it and by camera?
Yeah, it's got a camera system on it. It's got some laser systems on it as well, which are used for assisting the landing onto the blade. But it's mechanically set as to what thickness will be applied. And because everything else is highly controlled in terms of its orientation onto the leading edge and its distance, it hasn't got the variability anyway that you'd get with a manual operator.
So it's also touching the blade?
Yes, it's touching the blade, yeah. It's got little tiny wheels, outrigger wheels, which were within that U shape, which clamp onto the surface of the blade outside of the area that you're coating.
Very good presentation. What happens to the material you grind off and the solvents and so on?
Goes into the sea. No, it's not at the moment. So this is one of the problems because I think you talked about this sustainability and the plastic and all that. But all of these blades, what's falling off is going into the sea. They are looking at potentially metal protection strips like they use on helicopter blades. But the problem with that is just the coefficient expansion of thermal expansion is massively different, and it's not as trivial a problem as you might think.
Could yours not collect the weight?
Yeah, I suppose it could. I'll take that back to the developers, but it's a good point, and it's probably not. The only problem I can see is that you might need to do the grinding operation with some sort of vacuum collection system, and then comes back to base, empty that, plug in the cleaning modules and the coating module, and then take off. Otherwise, you'll go over the weight limit. And we're really keen to try and keep to this weight limit because it makes operating it so much more simple. But that's a really good. I'm going to take that back.
Thank you. I think we'll finish questions there so we get some lunch. We're 5 minutes early, so can we come back 5 minutes early and then we'll finish on time? Is that okay? So we'll come back in 1 hour at 2:20. But thank you very much, Chris.
Thank you.